Given the inefficiency of Bayesian optimization for model identification when you have very high dimensional spaces, like when you have an object with multiple components, or when we have a lot of objects in the scene, I became very interested in using differentiable physics for identifying the friction and the mass distribution of an object directly from observations, by computing analytically the gradient of the motion with respect to these unknown mechanical properties. So this is becoming very trendy and very popular these last years. And I'll be presenting one of the ideas along those lines. So this is an experiment that I will be using in this part, where we have an object that we cannot grasp directly, and we want to grasp it by pushing it first on the edge of the table and then picking it from there. But we want to be very careful for not pushing it over the edge. So we need to know the mechanical properties of the objects, basically. And for example, if you want to push a hammer like this from an initial configuration to target configuration, even if it's just nearby, you're going to need to know the distribution and the friction of the object at each part of it. And this is going to help optimizing the pushing actions. For example, choosing the point where you want to push it, the velocity, the force, etc. So we can start with playing with the objects again, with the robot, and observing how they are moving, and recording the image, and then from there we want to identify the properties of the objects from these observed motions. So the first thing we can do is take each object and decompose it into a large number of cuboids, and each cuboid is different, can be different from the others. It has its own mass, its own inertia, and its own friction coefficient. So you can do this with any object. Basically, you can just decompose it into a large components, and each one of them becomes like an individual object that is attached to other objects, which are the adjacent cuboids. So each cuboid is denoted by Cij here. It has its own mass, its own friction coefficient, its own inertia matrix. And this is an overview of the proposed method. So first you're going to push the object from some configuration to another one. You're gonna model the object as a set of cuboids, as I said. And then you can replay in simulation the physical actions that you execute on the real object, and then you will notice the differences between simulation and reality, the difference between the actual poses that happen on the real object and the poses that happened in simulation. And this constitutes what we call the simulation to reality gap, that will be minimizing by computing the gradient of the gap with respect to the physical parameters. So obviously, as I said, we cannot use Bayesian optimization because this is a combinatorial optimization problem in a large space of parameters, because we have a lot of cuboids here, and they are all related to each other. They all contribute to explaining the motion of the object. So if you look into traditional physics engine, what you have was on the left side as an input, you have state at time t, which is position and velocity of each cuboid. You have the action that is applied on the cuboids. This is the external force, or the force that's being applied by the robot, and gravity also. And we have also physics parameters, which are the masses and frictions of each cuboid. You give this to the physics simulator, and you get at the output, you get state at time t plus 1. But what if, in addition to that, we also get the gradient of the state with respect to physics parameters? That can help us compute the gradient of the reality gap, which is nothing but the difference between the true state and predicted state with respect to the physics parameters. And to do this, you can need to first compute the difference between true state and predicted state, and you multiply the result by the derivative of the predicted state with respect to the physics parameters, which are the mass and friction of each cuboid. And if you have differentiable physics engine, then you can get all that, and then you can use the gradient to update the physics parameters. So this is how we're going to model all the external and the internal forces on the cuboids. So first thing, we have gravity, and then we have also the force that's being applied by the robot for pushing the object. And then we can represent explicitly all the internal forces that are happening inside this object. So basically, each cuboid is applying a force on its neighboring cuboids, and the torque, of course, because there is also rotation. And this force could be pushing or pulling or the cuboids that are adjacent to it. And these need to be modeled explicitly in the system. And then we have the friction, which is a force, external force applied from the support surface to each cuboid. So each cuboid is going to have different frictional force, individual frictional force. And the direction of friction force is based on the velocity of the cuboid at time t and the rotation. The magnet is going to be very different based on the multiple things. And so basically, if we take all these internal and external forces, we can model them as linear complementary problem, where we have the system of equations. And actually, the original idea for this came from Zico Coulter from CMU in 2018 or 19. They had the NIPS paper that explained something close to this. And this is an extension, a modification of that idea. It builds on top of that. So what we have here is the system of equations where we have the mass matrix. This is a big diagonal matrix where we have the inertia and the mass of each cuboid inside this matrix. So the dimension of this matrix is the size of the number of cuboids that we have. It's a very big matrix. And then we have the Jacobian that represents all the interactions between the cuboids. And then we have Jacobian that corresponds to the direction of the friction on each cuboid, and this is a function of their velocities, x dot t. Then we have the predicted velocity at t plus 1 or t plus delta t. And we have the external force, and then we have the mu, which is the vector of the vector of friction coefficients. We have slack variables, and we have also lambda in, lambda f, which are actually impulses or a kind of fake forces. Or lambda e is, lambda in, lambda f are magnitudes of impulses. And lambda e corresponds to the internal forces between the cuboids, and lambda f corresponds to the friction force. So we can solve this system using, there are a lot of techniques for solving linear complementary problems. And then you can, from there, predict the velocity at t plus 1, t plus delta t. And that way you can do forward simulation. But actually what we're interested in is the backward step, which is how to go from the loss into the mass and friction. So we derived analytically the gradient of the loss with respect to the mass of each cuboid. So the global loss, which is related to the motion of the entire object, with respect to the mass of each component of this object. And this can be written like this in a closed forms way, which is a very complex equation, but actually it's nothing by products and inversions of matrices. So it can be solved in polynomial time. And then we can apply this gradient on the mass, and then we can do gradient descent, and then we can identify the actual mass of each component. The last step is a projected gradient, so we want to put an upper bound on the maximum mass. And this can be seen as an inductive bias, basically. And then we can do the same thing with friction. So we computed the derivative of the loss with respect to friction coefficient of each component of each cuboid, and this gives us the closed form solution for this derivative that we can just apply directly to identify the friction. So these are some results. These are real objects that we had. The robots was pushing them, and then this is on what we have is the initial model, which is just uniform mass distribution. I'm showing here only the mass, and then this is what we get after one step of the gradient. The distribution of the mass. This is what we get after 2 steps, 3 steps. So excuse me, it converts pretty quickly to something that's pretty close to the ground truth. And this is interesting. So if you look into the first object, which is toolbox, on the left side we have metal objects which are heavier than the plastic objects that we have on the right side, and this is very difficult to tell from vision, but we are able to identify it from motion. The open book is also interesting because the one side is much heavier than the other one when you have a book which is open, and we managed to find something close to that. It's not exactly what we got as actually diagonal, and I think this is due to the fact that we are using only a very small number of examples, which is necessary for doing on-the-fly model identification in real time. You don't want to have a method that requires like 50 pushes or 50 actions in order to identify a model. So this is all obtained with just a small number of examples. As we can see here, these are different learning curves that we get with different amounts of training data. So if we use one example, which means that we push an object only once, it doesn't work really well. But actually, if we get to 5 examples, then we can converge to much smaller prediction error. And this is the error in predicting the motion of the object. And this is the error in predicting the motion of each cell of the object as a function of how many steps in the gradient descent we are applying. It converts pretty quickly. So we did, this is an example of the curves that we obtained for the book. For example, we compared with a lot of black box methods like CMIS, like Neldermead. We also did finite difference gradient, which is quite slow because you have to compute plus minus delta for each parameter, so it's really a lot of combinations. And then we also compared with automatic differentiation in Python. So you can actually automatically differentiate a lot of things if you implement them correctly using AutoGrade tool. And it didn't work very well. So although automatic differentiation, I think, is a way to go in the future, but if you can analytically derive your gradient in closed form, I think that's the best thing to do. You can just implement it like we did here. So auto differentiation was really slow. That was the big problem. So once we identify the model, you want to do something with it. So you want to get this hammer to the goal. And the big problem there is how to select the goal configuration. But if you have a model of the mass distribution, then you can choose a goal configuration that is stable. And so this is selected based on the model by the planner. And then you want to plan to go from initial configuration to the goal configuration. And do that, you can just use select the waypoints by using RRT, for example, algorithm. Then the question becomes how you connect these poses or how to go from one pose to the next one. And you can do that by doing some sort of local gradient on the contact point. So you start with your best guess, like what would be a very good heuristic for pushing a hammer from one configuration to another one, assuming certain mass distribution, like we see here in the heat map, something that we identified from data. That becomes the initial seed, and then you can apply a local gradient where you try just vary a little bit the contact point on the left and the right and see if how the error is changing, and then you can choose the point which is locally optimal. And then you apply that action on the real object. So I will just let you see this experiment. On the left side is what we get by using this model identification algorithm. And the left side is what we obtain by using assuming uniform mass distribution for the hammer. And all that was done autonomously without interventions. Both the identification process of the mass and the planning, selecting the goal and planning, and then doing selecting the grasp configuration, and then picking the hammer was done all autonomously. So you can see here that it's almost unavoidable to do this kind of mass identification. Otherwise, we cannot reason about stability of the object, and I think it's quite an important thing to do. All right, then these are just some quantitative results of the same experiment where we compare the proposed method versus when you use a uniform mass distribution, and this is the percentage of successful grasps that we got at the end. And you can see that actually putting an upper bound on friction helps a lot, because if you don't put it, then a lot actually of the rotations will be explained by high friction as opposed to high mass. And this is a problem that we solved in follow-up work. So we realized that actually it's almost impossible to disentangle the mass from friction parameters if you have very low velocity, obviously. You cannot explain the motion. You cannot say the object is moving a certain way because it has certain kind of friction distribution or certain kind of mass distribution. But what you can do is you can come up with probabilistic approach that gives you all possible combinations with different probabilities. So in some of them, the mass is going to be very high, friction is low, and the other ones the other way around. And you can have all probabilities of all these models. And then based on that, you want to choose the safest goal configuration to place the hammer in it or the object in it. This is if you are trying to preserve stability of an object. Then let's say you have 38% probability for this configuration, 0.23 for this one, and then 34 for the last one. And under each one of these models, you want to simulate the balance of the object in this configuration and compare it to other configurations. And then at each point, you can either label it as stable or unstable, and then you compute the probability of each one of these situations or configurations of being stable or being unstable. And then you pick at the end the one that has the highest probability of being stable. So the bottom line is that you don't care really about the mass distribution and friction distribution as long as you are confident that this hammer is going to remain stable when you put it on the edge, as long as you have very high probability of that. And and these are just experiments using same object and pushing it to the edge. And what we are comparing here is using what you get if you plan with uniform mass distribution, and that gives us the lowest success rate in terms of grasping success. And then what you get if you use the deterministic planning with identified mass. This is what we got before. And then the new method which uses probabilistic reasoning on top of the identified mass distribution. So basically, you don't want to identify a single model, but actually a set of possible samples. Each one of them would correspond to a joint combination of mass and friction maps, basically, or heat maps. And you want to choose the configuration that has the highest probability of being stable under this distribution. This is the last experiment that we did related to that, which is kind of a game where we place an object on the edge, and then we let it go, and then we went to predict if it's going to fall or not. Of course, as humans, we can easily do that, and we can see the outcome actually if the object falls or not. But what we are doing here is we put, for example, book in certain configuration, we take an image, and then we want to ask our model if it's going to fall or not. And of course, it's really difficult to answer this if you use deterministic model identification, because sometimes you have this kind of entanglement between mass and friction. The only examples that you have are sliding an object on the top, and then suddenly you want to predict how the object is going to behave in completely different configuration where it's hanging on the edge. But actually, if you use this probabilistic reasoning, where you consider the full spectrum of combinations between mass and frictions, and you want to compute the probability or likelihood that this object is going to fall based on this distribution, then the result that we obtained is that using this probabilistic reasoning gave us the highest accuracy. So actually 100% of the time, the planner was able, using the identified model, was able to predict if the object is going to fall or not. Versus when we just pick one solution and then we average that over multiple solutions, which is the orange histogram there, and then the blue one is what you predict if you assume uniform distribution of the mass. We also expanded this work into mobile robot, where we wanted to identify the friction parameters of each wheel. So this robot has 4 wheels, and each one has different friction parameters. And then based on the observed motion of the robot, we have a differentiable physics engine that we implemented, and we compute the derivative of the motion with respect to the friction of the wheels, and then we tune them on the fly. And then we adjust the motion of the robot based on that. And what we are showing here is the difference between the curve that we predict in simulation by using the identified friction and the actual motion of the robot in the real world. So this is still ongoing work with my colleague Mridol at Rutgers, and we compared here in terms of time efficiency with the proposed method using LBFGS here, gradient-based method. We compared it with black box methods, and naturally it's much more time efficient compared to black box optimization.